SwayamPrabha. Digital India. Educated India.
Wastewater treatment parameters in the textile industry, lecture number 16. Now let us look at the wastewater treatment parameters in the textile industry. We have been talking a lot about all these parameters in the past lectures as well. Wastewater treatment in the textile industry is crucial due to the significant pollution it generates. Various parameters are considered in the treatment process to ensure effective removal of contaminants before discharge. Some key parameters include pH. Textile wastewater often has fluctuating pH levels due to the use of different chemicals and dyes. pH adjustment is necessary to optimize the efficiency of subsequent treatment processes. So, this we have spoken quite in depth in the previous few lectures also, that pH adjustment is a must in order to proceed for the treatment process. Chemical oxygen demand, COD. COD measures the amount of oxygen required to chemically oxidize organic compounds in water. Textile wastewater typically contains high levels of organic pollutants, making COD a critical parameter for assessing pollution level. Now, if the dissolved oxygen is not enough and the organic pollutants are more in quantity, the degradation will not take place very easily. Biochemical oxygen demand or BOD. BOD measures the amount of oxygen consumed by microorganisms during the biological degradation of organic matter present in the textile effluent. High BOD levels indicate a high load of biodegradable organic compounds, which can deplete oxygen levels in receiving water bodies and harm aquatic life. Total suspended solids, TSS. TSS includes suspended particles such as fibers, dyes and other solids present in the wastewater. Excessive TSS levels can cause turbidity in water bodies, leading to reduced light penetration and adversely affecting aquatic ecosystem. And this we have talked in detail quite a few times. Color. Textile dyes contribute to the coloration of wastewater. Color removal is therefore essential not only for aesthetic reasons, but also to prevent light absorption and minimize the impact on aquatic life. Total dissolved solids, TDS. TDS refers to the total amount of inorganic and organic substances dissolved in water. Elevated TDS levels can indicate the presence of various pollutants and may require treatment to meet regulatory standards. Heavy metals. Textile processes often involve the use of heavy metal based dyes and mordants, leading to the presence of metals such as chromium, lead, cadmium and mercury in wastewater. These metals are toxic and can accumulate in the environment, posing risk to human health and ecosystem. Surfactants. Surfactants are commonly used in textile processing for tasks such as wetting, emulsifying and dispersing. Excessive surfactant levels can have adverse effect on aquatic organisms and may require specialized treatment. Salt content. Textile wastewater may contain high levels of salts due to processes such as dye fixation and finishing. Elevated salt concentrations can contribute to soil salination and affect the quality of receiving water bodies. Nutrients, nitrogen and phosphorus. Textile wastewater may contain nitrogen and phosphorus compounds from sources such as dyestuff and detergents. These nutrients can lead to eutrophication in receiving waters, promoting algal blooms and disrupting aquatic ecosystem. Efficient treatment processes including physical, chemical and biological methods are employed to address these parameters and ensure compliance with regulatory standards before discharge. So, these are major parameters which need to be removed. The COD, BOD, pH adjustment, TSS, TDS and nutrients like nitrogen and phosphorus and salt. So, these are the main culprits which cause the main pollution in the textile effluent. Now, let us see one by one. Influence of pH on wastewater treatment of textile effluent. pH plays a crucial role in the wastewater treatment of textile effluent due to its influence on various treatment processes and the behavior of contaminants. Here is how pH affects different stages of textile effluent treatment. Primary treatment. In the primary treatment stage, pH adjustment may not be the primary focus. However, maintaining the pH within a certain range can help in the removal of large suspended solids through processes like sedimentation and flotation. Chemical coagulation and flocculation. Coagulants such as alum or ferric chloride are commonly used in textile effluent treatment to destabilize suspended solids and facilitate their removal through flocculation. pH significantly affects the efficiency of coagulation and flocculation processes. The pH optimum for coagulation varies depending on the type of coagulant used, but typically ranges between 6.5 to 8.5. Deviation from this range can reduce the effectiveness of coagulation and result in poor solid removal. So, you see, for coagulation it is necessary to adjust the pH between 6.5 to 8.5. Otherwise, the coagulant will not be very effective. Moving on, what is the influence of pH on biological treatment? Activated sludge or biological filters processes rely on activity of microorganisms to degrade organic pollutants in wastewater. The pH of the wastewater influences the microbial activity and the efficiency of biological degradation as well. Most microorganisms thrive within a neutral to slightly alkaline pH, and that is between 6.5 to 8.5. Extremes in pH can inhibit microbial activity and impact treatment performance. Therefore, maintaining the pH within the optimal range is crucial for ensuring efficient organic matter removal in biological treatment system. So, both in coagulation and flocculation stage as well as in the activated sludge stage of biological treatment, pH needs to be well within 6.5 to 8.5 only. Anaerobic digestion. In some cases, anaerobic digestion is employed for the treatment of textile effluent to degrade organic pollutants and produce biogas. And this we have studied quite in detail in the last few lectures. But how does pH affect? Anaerobic digestion processes are pH sensitive, with an optimal pH range typically between 6.5 to 7.5, even lower than what we mentioned for coagulation and flocculation and for activated sludge. Maintaining pH within this range is essential to support the activity of methanogenic bacteria and maximize biogas production. Disinfection. After primary and secondary treatment, disinfection is often carried out to eliminate pathogens and ensure the safety of the treated effluent. pH can influence the efficacy of disinfection methods such as chlorination or UV radiation. Optimal pH conditions for disinfection vary depending on the specific method used, but are generally within the neutral range. Overall, maintaining appropriate pH level throughout the treatment process is essential to ensure the efficiency of various treatment steps and achieve compliance with regulatory discharge standards. pH adjustment may be achieved through the addition of acids or bases as needed to optimize treatment performance. As pH influences at every stage of effluent treatment, it is very crucial parameter. So, the bottom line is that pH is a very significant parameter which needs to be adjusted according to the process which the effluent is going through. And we have seen that for anaerobic it is even more sensitive, because the methanogenic bacteria are more sensitive to pH changes. So, it should be ranging from 6.5 to 7.5 only, whereas a slightly broader range is possible for coagulation, flocculation step and for activated sludge activity. Moving on, let us see what is the importance of COD in the treatment of textile effluent. COD, or chemical oxygen demand, is a crucial parameter in the treatment of textile effluent due to several important reasons. Indicator of organic pollution. COD measures the amount of oxygen required to chemically oxidize organic compounds in water. Textile effluent typically contains a high concentration of organic pollutants, and time and again we have been talking about this, originating from processes such as dyeing, finishing, printing and washing. High COD levels indicate the presence of complex organic compounds that need to be removed to prevent adverse environmental impacts. Treatment efficiency. Monitoring COD levels provide valuable information about the effectiveness of treatment processes in removing organic pollutants from the textile effluent. By tracking changes in COD concentration throughout the treatment process, operators can assess the performance of various treatment units and make adjustments as necessary to achieve desired effluent quality standards. So, COD is a very important parameter because continuously it needs to be decreased, and if it is not done so, then one would not know whether the treatment process is effective or not. Biological treatment optimization. Biological treatment processes such as activated sludge or biological filters rely on the activity of microorganisms to degrade organic pollutants that are present in the wastewater. COD serves as a key parameter for monitoring the organic loading rate and assessing the biodegradability of the textile effluent. Maintaining COD within optimal ranges ensures that microorganisms have sufficient substrate for growth and metabolic activity, leading to efficient removal of organic pollutants by their degradation. Regulatory compliance. Many regulatory agencies establish COD limits for discharge to surface water bodies to protect aquatic ecosystem and public life and health. Compliance with COD regulation is essential for textile industries to avoid fines, penalties and legal liabilities. By monitoring and controlling COD levels in effluent discharge, textile facilities can demonstrate environmental responsibility and adherence to regulatory requirements, because now the regulatory requirements have become very stringent. Textile manufacturers have to abide by the regulatory compliance. Process optimization and cost reduction. Effective COD management allows textile facilities to optimize treatment processes, minimize chemical usage and reduce operational costs. By understanding the relationship between COD removal efficiency and treatment parameters such as pH, coagulant dosage and hydraulic retention time HRT, operators can implement strategies to improve treatment performances and enhance overall process efficiency. If the processes are optimized, then there is less cost that is involved in the treatment of the effluent, because the process itself will not have so much of pollution loading because of the optimization. So, that is the main crux of the whole issue. In summary, COD serves as a fundamental parameter in the treatment of textile effluent, providing valuable insights into organic pollution levels, treatment efficiency, regulatory compliance and process optimization. Effective management of COD is essential for mitigating environmental impacts, protecting public life and ensuring the sustainability of textile manufacturing operations. So, if effective management of COD is done, it is definitely going to mitigate the impact of the textile effluent on the environment, and it will be protecting the public health and ensuring the sustainability of textile manufacturing operations. COD is always indicated as pollution loads resulting from each processing operation of various raw materials. And we saw in one of the lectures that in each of the textile processing steps, whether it is sizing, whether it is desizing, whether it is curing, whether it is mercerizing, dyeing or printing or even finishing, each one adds on to the load of the textile effluent. Thus, COD removal is needed with more effective treatment. COD removals from textile effluent are accomplished by many researchers using various types of reactor systems or via different process strategies. So, many new methods have come up, many existing methods have been improvised. So, the whole idea is how to effectively reduce the COD level. Biological oxygen demand, BOD, it is a critical parameter in the treatment of textile effluent for several reasons. Indicator of organic pollutant. Like COD, BOD measures the concentration of organic pollutants in the wastewater, but it specially quantifies the amount of oxygen consumed by the microorganisms during the biological degradation of organic matter. Textile effluent often contains high levels of biodegradable organic compounds derived from processes such as dyeing, bleaching and finishing. Monitoring BOD levels provides insight into the organic loading and pollution strength of the textile wastewater. Biological treatment performance. BOD is a particularly important issue in assessing the performance of biological treatment processes, such as activated sludge, biological filters, lagoons, which rely on microorganisms to metabolize organic pollutants. High BOD levels indicate a greater demand for oxygen by the microorganisms, suggesting a higher organic load that must be treated to avoid oxygen depletion in receiving water bodies. By monitoring changes in BOD concentrations before and after the treatment, operators can evaluate the efficiency of biological degradation and adjust treatment parameters accordingly. So, depending on the load of the organic pollutants, this adjustment has to be done continuously, because the microorganism have a limited source of oxygen in the dissolved form in the water, and if they do not have enough for it to consume, to be able to function, to degrade the organic pollutants, then the microorganisms will die due to lack of oxygen. Oxygen depletion and aquatic life. Discharge of textile effluent with high BOD concentrations into receiving water bodies can lead to oxygen depletion through microbial decomposition processes. This oxygen depletion can harm aquatic ecosystem by suffocating fish and other organisms that depend on dissolved oxygen for survival. Therefore, controlling BOD level in textile effluent is essential to prevent adverse impact on aquatic life and maintain water quality standards. Here also there is regulatory compliance. Regulatory agencies often establish BOD limits for wastewater discharge to surface water bodies to protect water quality and aquatic habitats. Compliance with BOD regulations is necessary for textile industries to meet environmental standards and avoid legal penalties. Monitoring BOD levels allow textile facilities to ensure that their effluent meets regulatory requirements and demonstrate environmental responsibility. So, it is very imperative that BOD should be assessed, and high BOD containing water, wastewater should not be let out into the water bodies, because that is going to adversely affect the aquatic life of that water body. Treatment process optimization. Effective BOD management is crucial for optimizing treatment processes and minimizing operational costs. By understanding the relationship between BOD removal efficiency and treatment parameters such as aeration, mixing and hydraulic retention time, operators can implement strategies to enhance biological treatment performance and reduce energy consumption. Process optimization can lead to more efficient organic pollutant removal and overall wastewater treatment. In summary, BOD serves as a key parameter in the treatment of textile effluent, providing valuable information about organic pollution levels, their impact and treatment performance, regulatory compliance and environmental impact. Effective management of BOD is essential for protecting aquatic ecosystems, meeting regulatory requirements and ensuring the sustainability of textile manufacturing operations. Now let us move on to total suspended solids. What is their importance and how do they influence the pollution load in the textile effluent? Total suspended solids is a crucial parameter in the treatment of textile effluent for several reasons. Indicator of water quality, TSS, total suspended solid, refers to the concentration of suspended particles such as fibers, dyes and other solids in wastewater. Textile effluent often contains high levels of suspended solid due to processes like dyeing, printing and finishing. Monitoring TSS levels provides valuable information about the clarity and visual appearance of the effluent, which are important indicators of water quality. How if there is too much of suspended particle, the wastewater is bound to be turbid, cloudy and dirty looking. Therefore, by visual look itself one can say that this wastewater has too much of suspended particles. Impact on aquatic ecosystem. Discharge of textile effluent with high TSS concentrations into receiving water bodies can have adverse effects on aquatic ecosystems. Suspended solids can reduce light penetration into the water column, inhibiting photosynthesis and affecting the growth of aquatic plants. Additionally, sedimentation of suspended solids can smoother benthic habitats and disrupt the feeding and breeding behavior of aquatic organisms. So, it is both important for the aquatic plants and animal to carry on their biological activity within the water bodies. If suspended solids from the effluent are run into the water body, it is going to have very adverse effect. Clogging and treatment equipment. High TSS level in textile effluent can lead to clogging of treatment equipment such as screens, filters and pumps. Accumulation of suspended solids in treatment unit can reduce hydraulic capacity, decrease treatment efficiency and increase maintenance requirements. Therefore, controlling TSS concentrations is essential for preventing operational issues and ensuring the proper functioning of treatment facilities. Treatment process efficiency. TSS removal is a key objective of primary treatment processes, including sedimentation, flotation and filtration. Effective removal of suspended solids at the primary treatment stage reduces the organic and inorganic load on subsequent treatment units, improving overall treatment efficiency and reducing the risk of process upsets. Monitoring TSS levels allow operators to assess the performance of primary treatment processes and optimize treatment parameters as needed. So, you see, at every level these suspended solids need to be removed, and particularly at the primary level. Regulatory compliance. Now, everywhere there are regulatory norms for each of these parameters, and this we should understand and know for very well. Regulatory agencies often establish TSS limits for wastewater discharge to surface water bodies to protect water quality and aquatic habitats. Compliance with TSS regulation is necessary for textile industries to meet environmental standards and avoid legal penalties. Monitoring TSS level enables textile facilities to ensure that their effluent meets regulatory requirements and demonstrate environmental responsibility. In summary, TSS serves as a critical parameter in the treatment of textile effluent, providing valuable information about water quality, environmental impact, treatment process efficiency and regulatory compliance. Effective management of TSS is essential for protecting aquatic ecosystem, maintaining treatment system performance and ensuring the sustainability of textile manufacturing operations. So, it means that it is equally important that just like pH or COD or BOD, even total suspended solids have a very major and very important role to play in the mitigation of wastewater treatment processes. Now, importance of color in textile effluent. The color of textile effluent is an important parameter to consider for several reasons. The first one being aesthetic concern. That means, how does it look like? Color is one of the most visually noticeable characteristic of water. Discharging highly colored effluent can have aesthetic implications, especially if the receiving body is used for recreational purposes or has aesthetic value. High color levels in water bodies can create public perception issues and may be perceived as indicative of pollution, even if the effluent is otherwise treated to meet regulatory standards. So, suppose if the BOD has been taken care of, the COD has been taken care of, the TSS has been taken care of and the pH has also been taken care of, but if color persists, it is going to create a perception that the water is not safe. Light absorption and temperature. Colored compounds in water, particularly those from textile dyes, can absorb sunlight and increase water temperature. Elevated water temperatures can negatively impact aquatic ecosystem, affecting the dissolved oxygen levels, metabolic rates of organisms and overall ecosystem health. Therefore, reducing color in textile effluent can help mitigate thermal pollution and minimize its impact on the aquatic habitats. Ecological impacts. Some textile dyes contain substances that are toxic to aquatic organisms. Even at low concentration, discharging color effluent containing such dyes can harm aquatic life, disrupt food chains and degrade habitat quality. Additionally, certain dyes may persist in the environment for extended periods, posing long-term risk to ecosystems. Therefore, controlling color level in textile effluent is essential for protecting aquatic biodiversity and ecosystem integrity. So, what it means that overall it is not a good idea to run out colored water, because colored water is not just simply simple molecules. These textile dyes are very complex organic pollutants and they do not degrade easily. As a result, they create a very bad influence on the aquatic habitat. Regulatory compliance. Regulatory agencies often establish color limits for wastewater discharge to surface water bodies to safeguard water quality and aquatic habitats. Compliance with color regulation is necessary for textile industries to meet environmental standards and avoid legal penalties. Monitoring and controlling color levels in effluent discharge ensure that the textile facilities comply with regulatory requirements and demonstrate environmental responsibility. Treatment process optimization. Addressing color in textile effluent often requires specialized treatment processes such as advanced oxidation, flocculation and coagulation, or activated carbon adsorption. Optimizing these treatment processes to effectively remove color can improve overall treatment efficiency and reduce environmental impact. Process optimization may involve adjusting treatment parameters, selecting appropriate treatment chemicals, or implementing advanced treatment technologies. So, what it means is that the processes that are chosen for specifically for color removal must also be optimized, in the sense that the chemical dosing for coagulation or flocculation that is required should be optimal, because it should not generate more sludge, and therefore, treatment process optimization becomes very important and imperative. In summary, color is an important parameter in the treatment of textile effluent due to its aesthetic, ecological, regulatory and treatment related implications. Managing and reducing color levels in effluent discharge is essential for protecting water quality, aquatic ecosystems and public health, as well as ensuring regulatory compliance, sustainability in the textile manufacturing operations. So, we have seen that all these parameters, so far in this lecture we have discussed what is the importance of pH, what is the importance of COD, what is the importance of BOD, what is the importance of TSS and also color. These are the main parameters which are responsible for the pollution load in the textile effluent, and time and again I have been emphasizing about their importance and how and why they should be removed. Importance of total dissolved solids TDS in textile effluent. Total dissolved solids in textile effluent are important for various reasons. Water quality indicator. TDS represents the total concentration of inorganic and organic substances that are dissolved in water. In textile effluent, TDS can originate from various sources such as dyes, finishing agents, salts and other chemicals used in textile processing, which are water soluble. Monitoring TDS levels provide valuable information about the overall chemical composition of the effluent, serving as an indicator of water quality and pollution load. Environmental impact. Discharge of textile effluent with high TDS concentrations can have adverse environmental impacts on receiving water bodies. Elevated TDS levels can increase water salinity, affect aquatic organism, osmoregulation processes, and disrupt freshwater ecosystem. Additionally, TDS can contribute to soil salination if effluent is used for irrigation, leading to reduced soil fertility and reduced crop productivity. So, it is a major issue that TDS also needs to be taken into account equally as what the other parameters have been taken into. Corrosion and scaling. High TDS concentrations in water can accelerate corrosion of metal pipes, equipment and infrastructure in water treatment facilities and industrial processes. Furthermore, TDS can contribute to scaling and fouling of equipment surfaces, reducing operational efficiency and increasing maintenance cost. Therefore, keeping a good control of TDS level in textile effluent is essential for preventing corrosion related damage and maintaining the integrity of infrastructure, because these infrastructure are very costly. They are one time cost expense for the textile manufacturers when he is setting up his unit, and if they get corroded, then they will be needed to be replaced. So, that is additional cost then. Regulatory compliance. Regulatory agencies may establish TDS limit for wastewater discharge to surface water bodies or for reuse purposes to protect water quality and aquatic habitats. Compliance with TDS regulation is necessary for textile industries to meet environmental standards and avoid legal penalties. Monitoring and controlling TDS levels in effluent discharge ensures that textile facilities comply with regulatory requirements and demonstrate environmental responsibility. Treatment process optimization. Here also, TDS can affect the performance of various treatment processes, including membrane filtration, ion exchange and reverse osmosis. High TDS concentration may require pre-treatment or specialized treatment methods to achieve desired water quality standards. Optimizing treatment processes to effectively remove TDS from textile effluent can improve treatment efficiency, reduce energy consumption and enhance quality of treated effluent. So, everywhere we have been again and again talking about process optimization. In summary, TDS in textile effluent is an important parameter that impacts water quality, environmental sustainability, infrastructure integrity, regulatory compliance and treatment process efficiency. Managing and controlling TDS levels in effluent discharge is essential for protecting aquatic ecosystem, public life, public health and environment, as well as ensuring the sustainability of textile manufacturing operations. Now, what is the influence of heavy metal we have been talking that heavy metals are also one of the major criteria in the pollution load of the textile effluent. How do they influence the textile effluent? The influence of heavy metals in textile effluent is multifaceted and can have wide ranging impact on both the environment and the human health. Here is a more detailed look at some of the key influences. Environmental pollution, undoubtedly it causes pollution. Heavy metals, when discharged into water bodies through textile effluent, contribute to environmental pollution in a big way. These metals can persist in the environment for a long time, contaminating soil and water and disrupting ecosystems. Aquatic organisms such as fish, invertebrates and plants can be particularly sensitive to heavy metal pollution, leading to population declines and biodiversity loss. Bioaccumulation and biomagnification. Heavy metals have the ability to accumulate in living organisms through a process known as bioaccumulation. Organisms absorb heavy metals from water or food sources, and these metals accumulate in their tissues over time. Additionally, heavy metals can undergo biomagnification, where the concentration of the metal increases as it moves up the food chain. This means that top predators, including human, may be exposed to high levels of heavy metals through the consumption of contaminated organisms. Now, this has been a very serious problem, because arsenic has been a serious problem, mercury has been a very serious problem in aquatic habitat, and when fishes of these aquatic habitats were consumed by human being, it went into the food chain of the human being as well, and then it bioaccumulated and showed its manifestation. Health risk. Exposure to heavy metals in textile effluent contaminated water can pose significant health risks to human. Chronic exposure to heavy metals such as lead, cadmium, mercury and chromium can result in various health problems, including neurological disorder, kidney damage, respiratory issues, reproductive problems and even cancer. Children and pregnant women are particularly vulnerable to adverse effects of heavy metal exposure. Soil contamination. Heavy metals from textile effluent can also contaminate soil, especially if the effluent is used for irrigation or if runoff from the contaminated water bodies reaches agriculture land. Contaminated soil can affect crop growth and quality, leading to reduced agricultural productivity and potential food safety concern if crops take up heavy metals. Regulatory compliance. The presence of heavy metals in textile effluent often necessitates compliance with environmental regulations and standards set up by the government agencies in a very stringent manner. Industries may be required to monitor and limit the discharge of heavy metals into water bodies, implement wastewater treatment measures and adhere to influence quality standards to avoid legal repercussions and penalties, because this is much more serious when it impacts the human health. Technological challenges. Removing heavy metals from textile effluent during wastewater treatment can be technically challenging and costly. Conventional treatment methods may not be sufficient to effectively remove all traces of heavy metals, especially if they are present in complex chemical forms. Advanced treatment technologies such as chemical precipitation, ion exchange, adsorption and membrane filtration may be required to achieve the desired reduction in heavy metal concentrations. Overall, the influence of heavy metals in textile effluent is significant and underscores the importance of implementing effective pollution prevention and control measures to minimize environmental and health impacts. This includes adopting cleaner production practices, implementing efficient wastewater treatment technologies and promoting sustainable approaches to textile manufacturing. And now the time has come where the textile manufacturers are avoiding using any metal related dyes, so that they do not contribute to the organic load along with the heavy metal contamination. Now, what is the influence of surfactants, as that is also one of the parameters in textile effluent which has to be taken into consideration. Surfactants, which are compounds that lower the surface tension between two substances, are widely used in various stages of textile manufacturing, including washing, dyeing and finishing. Their influence on textile effluent can be significant and multifaceted. Cleaning and wetting. Surfactants play a crucial role in textile processing by aiding in the cleaning and wetting of fibers, fabrics and dyestuffs. They help to remove impurities, oil and other contaminants from the textile material, ensuring uniform wetting and penetration of the dyes and chemicals during processing. Foaming. Surfactants can contribute to foaming in textile effluent, especially during washing and dyeing processes, where agitation and aeration are involved. Excessive foaming not only reduces the efficiency of wastewater treatment processes, but also increases the risk of overflow and spills in wastewater treatment facilities. Biodegradability. The biodegradability of surfactants is an important consideration in textile effluent management. Biodegradable surfactants can undergo microbial degradation in wastewater treatment system, reducing their environmental impact compared to non-biodegradable counterparts. However, some surfactants may persist in the environment and accumulate over time, leading to potential ecological and health risks. Toxicity. Certain surfactants, particularly those containing alkyl phenol ethoxylates, APEOs and other hazardous compounds, can pose environmental and health risks. APEOs, for example, are known as endocrine disruptor and may have harmful effect on aquatic organisms and ecosystem. Effluent containing toxic surfactants can contaminate water bodies and affect aquatic life, leading to reduced biodiversity and ecosystem health. Effluent treatment. Surfactants can interfere with wastewater treatment processes by forming stable emulsions, reducing the effectiveness of coagulation, flocculation and sedimentation. Additionally, some surfactants may inhibit the activity of microorganisms in biological treatment system, affecting the overall efficiency of biological degradation processes. Regulatory compliance. The discharge of surfactant in textile effluent is subject to regulatory limits and standards set by environmental agencies to protect water quality and aquatic ecosystems. Industries are required to monitor surfactant concentrations in their effluent and ensure compliance with the applicable regulations to avoid legal repercussions and penalties. Sustainable alternative. In response to certain about the environmental impact of surfactants in textile effluent, there is a growing interest in developing and adopting sustainable alternatives. These include bio-based surfactants derived from renewable sources as well as innovative process technologies that minimize the use of surfactants or enhance their biodegradability. In summary, surfactants play an important role in textile processing, but their presence in effluent can have environmental, health and regulatory implications. It is essential for textile manufacturers to implement measures to minimize surfactant usage, choose biodegradable and environmentally friendly alternatives, and adopt effective wastewater treatment technologies to mitigate the impact of surfactants on the environment and public health. The influence of salt. Salt content has also a major and significant influence on the environment. Therefore, it has an environmental impact. High salt content in textile effluent can pose significant environmental challenges. When discharged into water bodies, elevated levels of salt can increase the salinity of the aquatic ecosystem, leading to adverse effect on the aquatic life and organisms such as fish, invertebrates and plant. High salinity can disrupt the osmotic balance of the aquatic organism, impairing their ability to regulate water and iron level, which can ultimately lead to physiological stress, reduced growth rates and even mortality. Soil salination, we have already discussed that if it is too high laden with salt, then the productivity, the agricultural productivity gets affected. High salt content creates corrosion in the industrial equipment and infrastructure, and therefore, in the textile manufacturing processes, this becomes a serious problem. Corrosion can lead to equipment malfunction, reduce operational efficiency and increase maintenance cost. Therefore, effluent treatment becomes imperative. Presence of salt in textile effluent can affect the performance of wastewater processes. High salt concentration can interfere with coagulation and flocculation. Regulatory compliances are there for even salt limits, and therefore, process efficiency is highlighted. In textile manufacturing, salt is commonly used as dyeing auxiliary. However, textile manufacturers may need to optimize their dyeing processes to minimize salt usage while maintaining product quality and process efficiency. So, in conclusion, we can say that effluent parameters in textile effluent encompasses a range of substances and characteristics that can significantly impact both environment and human health. COD, BOD, pH, color, heavy metals, surfactants and salt content. By addressing effluent parameters comprehensively, the textile industry can minimize its environmental footprint, ensure regulatory compliance and promote sustainable development. With this, we have come to an end of this lecture. Thank you.